We have begun. We are recording. What more can you have? What more can you want out of that? All right, so chapter 30, homework quiz and master set. We were going to wait till after spring break. It is time. So I guess the 29th and the 31st are next week. I'm thinking chapter 30 homework quiz a week from today.
Yeah.
That sounded enthusiastic.
Yeah.
I mean, what happened? Half the class, well. Now we can shift the sides, I guess.
Yeah, I think.
Oh,
next-
now that we've increased in size. Yep.
Yeah, so I think next Tuesday for the quizzes and then Thursday for the master set. Next
Alright.
Thursday.
Any objection? Any markers besides this?
When will we get our test back?
Today, unless I completely forget about it at the end.
Okay.
Yeah, they're in my office. So, homework quiz 30, and then master set 30. And I believe there's no master set for 31.
Correct.
All right, any other questions? We should be able to take care of chapter 31 easily enough today and get into 32. All right, so let's talk a little bit about magnetic flux, or revisit it. What's the symbol for magnetic flux?
Capital Phi. Sub B.
Yeah. And your textbook uses B. Some textbooks will use M. And the formula?
Yes.
B dot A, or B dot DA.
Yeah, well, if we can do the calculus version, we got DA. And so, and part of this is, I recognize as a repeat, but when we're dealing with electric flux, if I have a closed surface, that the electric flux through that surface, through any closed surface, is equal to the charge enclosed, usually with an E, the charge enclosed divided by some constant. And that's because we can have a charge all by itself, but you really can't have a north pole without a south pole. And so Gauss's law of magnetism says that if the magnetic flux through any closed surface, since it'll always have a north and south together, it's going to be equal to 0. Whatever. But that's through a closed surface. And so something of actually more importance to us is the magnetic flux through an open surface. So why don't we go through an example there? Let's just start out with a simple example, and then we'll get to the more complex one. So I've got I have some sort of area here. Arbitrarily pick it, let's make it 2 meters by 3 meters and a magnetic field of 5 Tesla. And so the magnetic flux, well, we can go to our definition right here, but since B is constant, we can pull it out. Since B and A will be parallel to each other, because remember the area vector is perpendicular to the surface, and B is perpendicular to the surface coming out, we end up with a magnetic flux. Oh, let's just add some formality to it, so B dot dA, B dot dA, B dot A, dA. In the second example, we will not be able to pull B out. And so therefore, we end up with just 5 Tesla times 3 meters times 2 meters. Then we end up with a magical number of 30 Weber. Pronounce it Weber. There's only one B in there, I believe. I guess it could be Weaver or Weber. I'm still going with Weber. Any questions on just the basic problem? All right. I don't know what you're thinking. You're going, that's great. But suppose the magnetic field is not constant over the entire area. How do we deal with it? I'm glad you asked. So I have some current flowing through a wire that we will consider to be infinitely long, and I have an area now over here, and I want to know what is the magnetic flux through this surface because of the wire. Now we will keep it simple enough to keep so that the current is constant, but the magnetic field definitely is not constant across this. And despite the way I drew it, this is supposed to be a rectangle, where this side right here is parallel to the wire. And let's go ahead and throw some numbers in here. So let's make this 5 centimeters, and then the width here, 7 centimeters, and the length, or the long way, 12 centimeters. Actually, 14. And I'm just going to call this surface alpha. So the magnetic flux through alpha. That's the question we're dealing with. Because B is not constant throughout the whole thing, we won't be able to pull it out, and so we're going to have to deal with that. At least the dot product is still an easy thing to deal with now. What is the direction of the magnetic field going through this surface? Hoping at least half of you will take a venture. Yes, you're right. Sorry, you missed my subtle nod before.
It's going in.
Why in?
Same reason because of that one. Previous one we was doing what he said, because.
I had this magnetic field is coming out. Those are dots in theory.
Oh, it's coming out. Oh.
And these magnetic fields were coming out, and the reason they were coming out is because dots are just easier to draw than X's. So I made this come out.
Okay.
I'm not creating the magnetic field the current is.
Okay.
So how do you determine the direction of a magnetic field created by a current?
your thumb is the direction of current and your fingers curl in that direction of the field.
Right hand.
Yeah.
So current's flowing this way, so my magnetic field is coming out on top. It's going into the board down below, and then in front it's going that way, and in the bathroom it's going up. So it's basically circling around like this.
Oh, like I see, I know what you're talking about.
Okay. So it is, and as usual, the stunning effects on the magnetic field. It's like they have the pox. Are you there, Devon? Okay. All right, so out on top, in on the bottom. There are other ways to get to the exact same place, but if that's good for you, you can go with that. Now, the closer you are to the wire, the stronger the magnetic field, which makes sense. Things are usually stronger the closer they are to the source. What is the formula for the magnetic field created by the current? Now, understand you haven't had the flash quiz yet, so by next Tuesday you'll know it like that. However, for right now,
I know the first part is B naught over 4 pi. No, that's.
oh, you're thinking of Biot-Savar's law.
Yeah, no.
Yeah, we can skip past that. Yeah, if you want to do it from scratch, yeah, go for it. However, there's a shorter version.
You said if we're assuming it's infinite, the line, you said with an infinite line?
Yeah, so at least long enough for us to consider it as such.
U naught I over 2 pi r?
Yep.
Okay, yeah. I guess we're not at this case.
Where r is the distance from the wire. That 2 pi r comes from the fact that if there is a circle that is the same distance, that equidistant from there, and the magnetic field, there's no reason for the strength of the magnetic field to be any different, 2 meters above it as it is 2 meters below it, or 2 meters to my right, or 2 meters to my left. So we know the direction is out, and we know that the strength of the magnetic field from what we're considering an infinitely long wire. So we'll just come back over here and erase the parts that don't apply, with just basically that. That still holds. So this is mu naught I over 2 pi r. Now, the area vector is perpendicular to the board here, because it's perpendicular to my surface, and the magnetic field is also perpendicular. So, add some flexibility in the direction I want for my area vector, but I'm going to have it coming out. And so I'm just going to make that dot product go away. Technically, there's a cosine of 0 in there, where that's the angle between my magnetic field and my area vector. But that's just 1. So we need to somehow get this in terms of a single unknown. U naught is a constant. It's the permeability of free space. I, the current, is constant just because I'm making it such. 2 pi obviously constant. So I'm going to pull that stuff out. But I'm left with my distance from the wire, which does vary, and dA, which automatically is a variable from the fact that it's my differential and my integral. And I need to get these in terms of the same variable. I'm going to take one shortcut here. I am going to assume that the magnetic field at this location right here is the same as the magnetic field at that location. that anywhere, as long as you're from the same distance away, the magnetic field is constant, as long as I'm a constant distance away. So I'm just going to treat that as my infinitesimally small area. And this distance here would be R. Well, it's just a rectangle. It's just a really skinny rectangle, but it's still a rectangle. So my length of my rectangle is 14 centimeters. What's the width of my rectangle?
DR.
Yes, it is. I'm gonna leave L in it just because it's less writing than 0.14. But L is a constant here. So my dA is just L times dr. So I get mu naught I times L over 2 pi, integral of 1 over r dr. I now have it in terms of a single variable. I can now do limits of integration. So what's the smallest value of r? And without even knowing what the question is, Gage is going to give me the right answer now. You had a chance to impress everyone in here.
Sorry.
You'll have other opportunities.
About 5 centimeters.
Yeah, because we're concerned about the area, about what's going on in this area right here. R is the smallest value in order to get into it, which is 5 centimeters.
So the largest would be 12 centimeters?
Yes. Which is why I changed the 14 centimeters, why I changed the length to 14 centimeters from 12 centimeters, is I just didn't want 12
So
shown
then,
twice.
cause that magnetic field in there is consistent from the bottom of that plate to the top of that plate.
Yep, absolutely. So now we got the calculus problem, integral of 1 over r dr.
Natural log of R.
Now, I hope all of you recognize that, and if not, learn it, don't memorize it, whatever you need to do. Or I guess potentially it's not math class, so you could ask. But. Then we'll have to the natural log of r from 0.05 to 0.12, which becomes mu naught I L over 2 pi times the natural log of 2.4. Yeah, feel good about that. And so now it's just a matter of plug and chug. So we have 4 pi times 10 to the negative 7th times my current, which I never gave. Or we'll not use it, let's make it 3 amperes. Times my length, which is 0.14 meters. Divided by 2 pi times the natural log of 2.4. And someone would be kind enough to crank that out. And then when you give the answer, throw in some units if you're feeling of the mind to do it. And if you're not, hopefully someone else will. Or we will just sit here in awkward silence.
What did you throw in for mu naught?
That's 4 pi times 10 to the
4 pi,
negative 7.
okay.
I got, 7.35 times 10 to the negative 8 Webers.
Does anybody agree with them?
I got the same thing.
All right, groundswell of 2, we got, I guess 3, Joseph gave a nod.
I didn't do it, but. I was
Oh, you
trying.
just believe him?
Yep.
I had it to the negative 7th, I don't know why,
You did the negative 7 here?
yeah. Trying to figure out why.
Like I said, negative 8.
I got 7.26 to the negative 7. 4, 5, 2.
I got 7.35 times 10 to the negative 7.
I got 4 pi.
I might have,
times 10 to the
oh,
negative
that's what I
7.
did, I did times 1.4 instead of 0.14, so it is
Ah, okay,
negative 8.
so I guess Enrique's the last one to convince.
That's ln 2.4, right?
Sorry, that's natural log of 2.4. That's 0.14. That's 3. For some reason, I decided to throw units into that one.
Yeah, I'm doing the same thing. I mean,
Did you do, when you did this, did you get parentheses around 2 pi, or did you do just divided by 2 pi?
yeah, I just put divided by 2 pi.
So then it divided by 2 and multiplied by pi.
So divide by pi twice.
Okay.
Yeah. If you divide it by pi twice, then there's another issue involved. Now, this kind of thing will show up again. The fact that we